So this is the first video we're going to do in sort of thinking about how we deal with derivatives of functions in more than one variable. And in particular, what I want to do in this video is just go through a little bit of both how you calculate and how you interpret partial derivatives. So we're dealing with this sort of idea of partial derivatives, and notationally a partial derivative is typically denoted in a couple of ways. So if I have some function that depends on multiple variables, so let's say it's a function of x and y, I might denote partial derivatives of that as f sub x and f sub y, which denotes the partial derivative with respect to x or the partial derivative with respect to y. Or I might also denote the partial derivative with respect to x by writing the delta, so delta f over delta x and delta f over delta y, where these are lowercase Greek deltas. So notationally, those are sort of the two common notations you'll see for partial derivative. So that's sort of part one, is notation. A second component of this video is not just how do we denote it, but what does it actually mean? And the meaning of the partial derivative is fairly simple, in that it's simply asking the question, how fast is the function changing with respect to that variable if you hold the other variables constant? So the partial of f with respect to y is asking the question, how fast, or what's the rate of change with respect to the variable y if you hold all the other variables constant. And so let me just talk about a sort of simple example of that. Let's say our function of x and y is simply x times y. Right? And we could ask the question, okay, what's the partial derivative of that? In other words, how fast is x changing with, how fast is the function changing, how fast is f changing with respect to y if we hold x constant? When we think about what x times y looks like, so here's x and here's y, and we're sort of imagining this function x times y on that evaluated on the plane. Well, pretty clearly x times y is 0 at the origin, right? As we move along the y-axis, it stays 0 all the time. As we move along the x-axis, it stays 0 all the time, right? Because when x is 0, it's 0. When y is 0, it's 0. When we say we go to y equals 1, right, and we move along the line y equals 1, what happens? Well, we move along the y equals 1, it's going to get larger and larger and larger as we move to the right, because 1 times x is going to get getting larger. It'll get more and more negative as we move to the left. Similarly, if I move along the line x is equal to 1, when I start out at the x-axis, on the line y equals 0, and I move up along this line, x times y is going to get bigger because x is equal to 1 and y is increasing, so it'll get more and more positive in this direction, more and more negative in this direction. So when I ask what's the partial derivative with respect to y, I need to actually ask that question for some given point. So if I ask the question, say here, what's the partial derivative with respect to y here, that tells me how fast the function is changing if I were to walk in this direction along the constant x line, along this contour of x equals 1, right? So in this case, I would look at this and I'd say, okay, well, it's increasing, and the rate at which it's increasing, well, x is equal to 1 as I walk along that line, y is just y, so 1 times y. So the partial with respect to y would actually simply be 1 along this line, because that's what the slope is of the function as I walk just along that line, right? If I, on the other hand, went out to this line where x is equal to 3, and I walked along that line, well, if I look at what the function is as I walk along that line, now I've got 3 times y, so the partial of f with respect to y along this line is equal to 3. Okay, so that's what we sort of mean by the partial derivative, is how fast is the function changing as we hold all the other variables constant and allow one variable to change. And finally, we want to talk in this video briefly about how to actually calculate the partial derivative, and I'll make a second video after this that does some more complicated examples, but for this video let's just do the simplest example. The way that you calculate the partial derivative is effectively you are taking the derivative of the function while pretending that all of the other variables are constant, right? So if I take the partial with respect to y of x times y, what I'm actually doing is imagining that x is a constant and taking the derivative of this constant x times y with respect to y. In other words, if I were doing d by dy of c times y, what would I get? I'd get c, and so the partial with respect to y of x times y is simply x. And if we sort of tie that back to our example here, we can see that along this line, where x is equal to 1, sure enough our slope of that line is 1, the partial of f with respect to y is 1, which is true along the line x equals 1. And similarly along here, x is equal to 3, and the partial of y with respect to x, with this partial of f with respect to y along that line is 3, which is also the same as what x is along that line. So that's all I want to say in this video, is sort of this idea of some notation for the partial derivative, the idea that you're asking the question, how fast is the function changing with respect to one of the variables while you hold the other variable constant, and the idea that at the core, the way that you actually go about evaluating what the partial derivative is you're treating the function of multiple variables as if the other variables were constants, and you're only taking a derivative with respect to the one variable you're taking the partial for.